Hello class, today we are going to start our unit on circles. And we're going to start with some vocabulary words associated with what a circle is before we can progress to so much to learn, just like triangles. We have a lot that you probably never knew were true with circles. Okay, so what is a circle? A circle is simply a set of all the points in a plane that are equidistant from a given point. That given point is what we call the center. All right, so if we were to connect from that centered point to any position on that circle that you are familiar with, you will see that we have this infinite number of equal distances that we call the radius. All right, so let's take a step back. Let's talk about how can we name that circle. When you name a circle, you simply identify the dot that appears to be in the middle of the circle, and you simply do the symbol that looks like a circle like that, and then you put a capital letter next to it. This is called circle C. The center is simply that position that we identified here that's right in the middle of the circle. And if I said name the center, you're going to pick that point, and it's always a capital letter. A radius is that distance from the center of the circle to any position on the circle. So that is the radius. And it's, you can see over here, I have multiple radii that we could, if I said name a radii, you're going to look for a segment that starts at the center and ends right on the circle. So this distance over here is called the radii. So if we were to name them, we have a couple that we can see. You can see you have this radii here, and you have another one here. And all radii, which represent the distance from the center to the circle, they're all congruent. So all radii are congruent for all circles within the same circle. So we have segment, and it is a segment. So remember how to name a segment. Don't forget it is 2 capital letters with a bar on top. And I have 2 listed here, CB, and I have AC. Now again, it doesn't matter the order when we name a segment. I could have switched these 2 around. Instead of AC, I could call it CA. Instead of BC, I could call it CB. Okay, but you do need to keep that bar on the top. Without the bar, remember, it represents the length of the radii. Okay, so the next one is, what does it mean to be a chord? A chord is also a segment, but the chord is a segment whose endpoints are actually on the circle itself. So an example, I have multiple examples of chords here. You have this chord here. Notice that it's a segment. Endpoints are both on the circle. Here's another chord. It's a segment whose endpoints are on the circle. So let's go ahead and name those. So one is, you have an X, Y, capital letters, and you have segment A, B, again, capital letters. All right, so if you look at this other illustration over here, this line that goes through the circle is not a chord, but it does contain a chord. If I were to put this little dot right there, a part of that line is a chord. So from S to T, that is also a chord. I just put that in the wrong spot. We're just going to move that right up here. There we go. Okay. All right, so the next vocabulary word that we have is called a diameter. A diameter is also a chord, but it is a chord that goes through the center. In fact, it is the longest chord for that particular circle that would be possible. So the only diameter that I have is this one right here. Notice the diameter goes through the center. And just a little extra side note, it is composed of 2 equal radii. And that will be something to note somewhere down the road as well, that we're going to be using a lot of that fact. Okay. All right. So to name, if I said identify in a diameter, the only one that is given is AB. And you only use 2 letters to name a segment. Do not put that C in the middle. Okay, next one is, we're going to be spending a lot of time between differentiating these 2 terms right here. One is called a secant and the other one is called a tangent. A secant is a line. Now we're going to use that very lightly here because secants don't necessarily have to be lines. It could be chords. But the main component of a secant is it does go through the interior just like a chord, but part of that segment or line, or could be even a ray, goes outside of the circle, all right? And it could exit out on both sides, but a portion of it could be outside. So it does touch the circle in two places, but it does go through it at some position. So we do use that a little bit lightly in our descriptor here. But if you look at the picture over here, this is an example of a secant. Okay, so you can see components of this line are outside. It does go through the interior, it slices through, it touches in two places, but it exits on either one side or both sides. Okay, but it does have to happen at least in one position. So if I ask you to name a secant, you're going to look for a line that goes through the interior and pops out. So an example would be line ST. Okay, tangent, on the other hand, yes, it does go through the circle and exit out, but it only touches the circle in exactly one spot. It doesn't go through the interior. It has no interior points. It simply touches and goes. All right, so that line that you see over here, VW, is what we call a tangent line to a circle. Now, what we're going to be very interested in throughout quite a few of our lessons is what we call a tangent point or point of tangency. So if I say, hey guys, that line is tangent, and I might ask you, what is the point of tangency? So the point of tangency is the point at which that line touches the circle. And again, it's only one spot right there. So point V is what we call the point of tangency. Okay. All right, so there you have some basic vocabulary. So really quick, what we're going to do is we're going to just go through this over here. I want you to pause the video, and I want you to test yourself to see what you remember. So just put me on pause for just a second, and I want to know, given each of these, identify whether the given geometric figure is a line, ray, segment, is it's best described as the radius, a chord, a diameter, a secant, or a tangent. Okay, so given each one of those, how would you describe it? Is it the radius, a chord, diameter, secant, or tangent of that circle? So again, pause me, and then come back, and let's check your work. Okay, pause. All right, come back. All right, so the first one we have is BC. All right, so this, notice it does not have any arrowheads. This is a segment. So I'm going to go to, where is segment BC? Here is B, here is C. Oh, and notice it includes the center, and it touches and it ends on the circle itself. That, my friends, we call the radius. Okay, next one is a line. All right, so remember, a line goes on forever. So when you look for EA, so identify where E is, identify where A is, and that, as you can see, if it's a line, it does go through the circle and exits, and it touches the circle in two places. The best way we can describe that is a secant. All righty, the next one is a ray. All right, so we start at D right here, and it goes in the direction of E. All right, now, we talked a second ago about lines being tangents. Now, rays can also be tangent. Okay, so if it takes on the characteristics of touching in only one spot without going through the center, that is tangent. So we can actually say that the ray is tangent. The next one is a line BC. If you find B and you find C, now remember those arrowheads mean that it's actually going to go through. You don't want to call this a radii because it actually will continue through forever and ever and ever in both directions. And when it crosses in two places and it goes through the interior, we call that a secant. All right, the next one you have AB. AB, notice there's no symbols on the top, has a beginning, it has an end. Oh, and look at that, it goes to the center. That is called a diameter. All right, now you always want to give the most specific name for it. A diameter is a chord indeed. So if you put chord, really the most, the best way that we want you to name it is the most specifically is the diameter. Even though chord would be correct, give the most specific. Lastly is segment, AF, it has a beginning, has an end. segment AF from here to here. Even though it's a part of a secant, if I ask you what does this represent, it is a chord. You're not going to call this a secant. So this is a part of that secant that we're asking, what do we call that? Okay. All right, outstanding. Let's move on. So the next part is determining, we want to know if the circles are tangent. All right, so what it means to be two circles that are tangent is, all right, so we can have a line, a ray, a segment tangent to a circle, but also two circles can be tangent to each other. So if you were to look at each one of these, remember tangent means it touches in only one spot. So if you were to look at all of these, which ones do you think are tangent circles? I'm going to give you just a second to think about it. 5, 4, 3, 2, 1. All right, so the circles that are tangent are the circles that touch in only one spot. That would be this one, and that would be this one right here. So only two, and I'm just going to write this right above here. The illustration in A and the illustration C would represent tangent circles, circles that touch in one spot. Okay. The next part of this question is asking us, tell how many common tangents that the circles have and then draw them. And then I want to know, are the tangents, are they internal or are they external tangents? Okay, so let's talk about what that means. First of all, when a tangent, remember, can only touch in one spot. But we want to know, is there any way we can draw a line that is tangent to both of the circles? All right, and they would share it. So I want you to imagine if I were to draw this line right here. This line right here appears to only touch in this position and this position. That would be called a common tangent. So I want you to think about, are there any others that I can draw? How many are there total that would be common? And then once we've identified that, then let's go ahead and talk about what does it mean to be internal and external. So what I want you to do right now is if you would take a few seconds, again, I want you to pause the video. I want you to draw all the common tangents. If you want, you can listen through while I do A. You can do it with me and then do the rest on your own and then check your work, however you want to do it. But I'm going to go ahead and get started on doing A. All right, so for the first one over here, I already started. I showed you this one. And what you want to do is be really careful. I do recommend that you use a straight edge when doing this, all right? And you might have to move it around a little bit, and you want to probably have a fine tip pencil when you're doing this because you don't want to go into the interior, because when I ask you to do this and I test you on this and assess you, I'm going to make sure that it doesn't go to the inside, and then I'm just going to kind of fill this in to make it look like it touches. All right, so that's a pretty good representation. Each of those dots I'm going to do in red, those are tangent points. Okay, all right, so I probably should have moved that line a little bit in, but I don't want to go inside either. All right, so I have another one. I could also go on this side and create that. All right, so over here, here's another common tangent. That line is tangent to both of the circles, so they share those two tangent lines. All right, so I don't know if anyone found this one, but there's one more. The next one goes right between those two. This is also a common tangent to the both, right at that point of tangency where those two circles were tangent to each other. So what I have here is a total of 3. And the question is, how many common tangents? There's 3. Now the question is, which ones are internal, which ones are external? If a tangent that is common goes between the two circles in any way, we call that an internal tangent line. So this one over here is internal. Internal. And the other two in green that you see, I'm going to put EXT for external tangent. So that's the 2 in green. Okay. All right. So now that you have a feel for what does it mean to be a common tangent, internal and external, go ahead and do the other 4 problems and then come back and check your work. Okay. You can go all the way to the end and then check after this. Okay. Or whatever you want to do. All right. So go ahead, pause me, and I'm going to do it in the meantime. All right. Pause, and now come back, and here we go. I got this one is a common external. I can't pause my video when I'm doing this, otherwise I would pause it and then I would go ahead and come back and do the problem with you guys, but it's not quite working this way. All right, and here's my points. And notice if I tried like the other one to go between the two circles, it's going to go into the interior, so that would not have any internals. So I have a grand total of 2 here, and they are both external. That's an external one, and that's external. Okay, here's another one. All right, so on this one over here, I'm going to just go vertically right here, and that one is common to both, and we would call that an external, and there's only one. All right, so if I were to draw on this next one a tangent to the outside one, it won't touch the inside one. If I touch the inside one, it becomes a secant for the outer circle. So this one has none. All right, and let's see how you guys did on this one. 1 external, 2 external, and trying to get it perfect for you guys. And put my little arrowheads in there. All right, so far we have 2 external. How many of you got this next one? Bum, bum, bum. If you were to draw here to here, this line, which I'm having a hard time with just getting perfect. That one, ooh, that wasn't too bad. Popped right into place, right where I want it. And this one, bum, bum, bum. All right, now I don't want this to look like it's going at all inside, so I got to be careful. All right, so I have this one, tangent here and here, this one here and here, and the blue one. How many were you able to get this? Wish I could see your hands right now. All right, so what we have is a total of 4 common tangents. And as you can see, the internal ones are in blue, and the external are what we see in green. So this one has a grand total of 4. Okay, yay. All right, now to the good stuff. Now that we know a little more vocabulary, let's talk about a theorem that we have. So we have this theorem that says if you have a line that is tangent to a circle, okay, so here's our line, line M, tangent to the circle at point P. What this theorem says that if you take the radii and connect it, the radius, to that point of tangency, so there's your radius, the theorem says that the radius is always perpendicular to that line at the point of tangency. So in a plane, a line is tangent to a circle if and only if, remember that's biconditional, if the line is perpendicular to the radius of the circle at its endpoints. So we can go both ways with this. We can say that if the line is tangent to a circle, a line is tangent, okay, if and only if the radius is perpendicular, and we can reverse it. If the radius is perpendicular to some line, then that line has to be tangent. Okay, so it does go both ways. Now, in this next exercise that we're about to do here is I would like to know, is our S tangent to the circle at point S? Now, the only way that this is going to be tangent is if this radius is perpendicular. Well, how do I know if it's perpendicular? The only way I know if it's perpendicular is if this is a right angle. Well, how do I know if it's a right angle? Well, if we do the Pythagorean theorem, the right angle would have to exist here. These two would have to be the legs of this triangle that I just created. So if we can show that 24 squared plus 10 squared equals this whole 26, which is from here to here, by the way, and it is listed, and I really want to emphasize that this whole thing is 26. If I can just show that this satisfies the Pythagorean theorem, where this is the potential right angle, then this has just proven that ST is tangent using the tangent to line theorem, or tangent line to a circle theorem. Okay, so we can do the test. So the test, once again, is you're going to do your Pythagorean theorem. is 24 squared plus 10 squared equal to 26 squared. All right, so you can go through the math. You can do all this. At the end of the day, you're going to say yes or no. All right, but there was another way we could have done this, and maybe some of you figured it out. Maybe not, but I'm going to keep going anyways. And this is the longer way to do this problem. All right, so if you remember something about our chapter 9, section 1, but over here you can see, yeah, these are both equal. Ta-da! Therefore, it's a right angle. But how many of you notice that 24, 10, 26 is a Pythagorean triple? Notice that if you were to simplify the ratio down here, the 24, the 10, and the 26 would simplify down to a, do you remember this? A 5, 12, 13 triangle, noticing that the 13 represents that numbers. It's in the right position. If you would have seen that, you would have been able to address this question right away. So what we can say right now is because angle S, all right, so we can say because angle S is a right angle, this implies that S, segment ST, is tangent to circle R. Okay, let's try another one. All right, so notice over here for this one, it says that UT is equal to 7. So that's this value right here, just from here to here. All right, so in this problem over here, the question is ST tangent to the circle? So it would only be tangent if RS was perpendicular. Okay, so what we have is we need to know all three side lengths of this triangle. We know RS, one leg is 5, the other leg is 12. All right, now be careful here. Now remember, all radii are equal. This is a radius and this is a radius. Now, if this is 5, this has to be 5. So this would have to be a total of, if you add them up, 7 plus 5 is 13. All right, so once again, you're going to ask yourself, okay, is this a triple? Okay, so if you were to go through this, you can see you have a 5, 12, 13. It is a triple. You have a 5, 12, 13 triangle, which is one of the ones that we asked you to memorize. And you can see right here, voila, it works out. Okay, it's a right triangle because it satisfies a triple. Okay, or it would satisfy the Pythagorean theorem. Alrighty then, so now let's go ahead and let's move on to our next problem. In this next diagram, we're moving on to example 4. It says in the diagram, B is a point of tangency. So right when you see that, the first thing you should say is, okay, if that's a point of tangency, that means that that's a right angle. So now what you have is a right triangle. And this question over here is asking us to find the length of the radius. All right, so we are trying to find these two equal parts here. And we've had similar problems like this in the past where you had a right triangle in terms of variables and you had to solve for the variable. So what we're going to do is we're going to do probably exactly what you anticipated. We are going to do the Pythagorean theorem to solve. So let's go ahead and get set up. So the Pythagorean theorem, we have legs squared. So I'm going to write up here 77 squared plus the radius squared is equal to, now be very careful, the hypotenuse is the sum of these two numbers. All right, so you have a binomial squared. So go ahead and get out your calculators and let's see how far you can get by solving this by yourself. So I'm going to give you guys a second to do that. And then I want you to pause and let's see algebraically how you do. On your mark, get set, go. Okay. And I will continue doing it while you do it on your own. But don't watch me. I want you to do this by yourself. All right, so you're 77 squared in your calculator. You get 5,929 plus your r squared. All right, so I'm going to go a little fast here. Binomial squared is an r squared. The first number squared, multiply the two together and double it, and that gives you a 98r. And then plus the last squared is 2,401. And now when you go to solve for r, what I want you to notice on both sides is that you have an r squared that cancels out. All right, so those go away. And then I'm going to go ahead and subtract the 2,401 from the 5,929. And when I subtract that over, I end up with 3,528. And then that equals 98R. Dividing both sides by 98, R is, 36. All right, so I just found the radius. If I wanted the diameter, you would double it. So there could be some additional information that I may want from you. Another bit that we could ask an extension on is finding the circumference and the area of the circle. So if you go back to circles, and when we talked about circumference in the past, it's kind of come and gone throughout our course so far. Circumference is 2 times pi times r. Again, I want the exact value, so we're not going to use our calculators at this point. So you're going to take 2 times pi times your 36 for a grand total of 72, and we're going to leave pi as a unit. So whatever the unit is, we're just going to leave it like that. Okay. And leave pi as your variable. You're not going to, it's not really a variable, but don't put it in your calculator. That's an exact value. The area is pi times r squared. So you have pi times 36 to the second power. Okay. And then go ahead and solve that. 1,296 pi units squared. Okay. There you have it. Alrighty, so the next problem is an application problem. So this problem over here is going to end up looking really close to example 4. Okay, so I want you to go ahead and I want you to do this problem. And I'm going to ask you to do this problem by yourself. And I'm going to get you just a little bit set up. All right, so I'm not going to do the entire problem because I really would like you to really try hard to go back. I'll give you a little bit of time to do that. And we'll talk about this one in class to see how you guys did. But what you have here is you are standing 36 feet from a circular swimming pool. So what I'm going to do is I'm going to put a little dot representing you here. All right, if you want, you can draw a little picture. Here you are. Oops, that's not working out too well. There you are. Okay, something like that. Alrighty, so you're standing, it says 36 feet from the swimming pool. So if I say, hey guys, go measure the distance to the wall. All right, so this is just a little side note. So if here's the wall and you're standing here and I say, what is the distance? All right, so are you going to draw a line over here? Probably not. When we talk about distance, let's recall, you're going to go straight to the object, straight on at a right angle. But however, how do you draw a right angle to a circle? Well, that doesn't happen. So if you wanted to go straight on, it's always going to be the shortest distance. And what you're going to aim for to find that shortest, closest distance, you're going to aim for the center. All right, so that would be almost equivalent to being perpendicular, even though it's not perpendicular. All right, so that is where you're going to be aiming, right here. So you're standing 36 feet from the circle. So what I'm going to do is I'm going to go ahead and draw that distance. And I am going to stop here, but then I'm going to dot it here. Okay, so you can kind of see that that line is an extension, all right? But the distance that we are given is 36 feet, would be right here, 36 feet, okay? And then it says the distance from you to a point of tangency on the pool is 48 feet. All right, so what we're going to do here is if I say tangent, from you to the circle tangent, you want to imagine a line coming off of you, and it's going to hit the circle tangent. All right, so remember, it goes past if we're looking at lines, but it only touches here. So when I draw this, I'm only going to draw from my body to the segment here. I don't have to continue beyond that. So this segment, we're going to imagine it could keep going, but we're just going to stop at the point of tangency. But that distance over here is 36. Now, when you think about it, it really doesn't matter if we go up 36 tangent or if we go down 36. Okay, it doesn't matter which way we go. And this is going to lead us into a theorem that we're about to do after this is, oh, that wasn't 36, I lied. That's 48. You guys would have caught it. You're probably, no, Miss Holbrook, stop. All right, so this is 48 feet. and this is 48 feet. Okay. All right. So now we have everything labeled, and just that thought of, I could have gone up 48 or I could have gone downward tangent. There's two possible tangents from my position that I could have potentially drawn. Okay. All right. So the next thing over here is they want to know what is the radius of the swimming pool. All right. So now you have to think about, all right, I have to draw the radius. I want a visual. Is this the radius? Well, yeah, that's a radius, but is there another radius that I can strategically draw that would allow me to solve for the radius? Well, we've already learned that if we connect strategically from the center to the point of tangency, we know that that gives us a right angle right at that position. So that little piece of information right there, that theorem that we learned on the front side there, is going to be crucial when solving this, because now what we are able to do is set up a right triangle where we're going to let both of these be R, and we're going to go ahead and we're going to solve for R. So I want you to go ahead and do that tomorrow in class. We were going to talk about this, and we're going to see how you guys do. So I want you to go ahead, boom, 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 solve for the radius. I do not need you to solve for the circumference in the area, but it is just like the problem above. Remember, you're going to take the leg squared plus the leg squared. The hypotenuse, don't forget, of this triangle is the sum of those two, just like we did here. Okay, so go ahead and finish that problem, and it'll be a good point to start with tomorrow. Okay, all right, in this next one, we have what is called the external tangent congruent theorem, which I tried to plant a seed in the problem above. And what this theorem says is if you have a circle and some external point, all right, so that would be you in this problem, then from this point, if you were to draw both common tangents from that position, then those would have to be congruent. And you could probably see it above just from what we talked about. All right, so tangent segments from a common external point, right? That would be like you above. Those are congruent. So let's do this application problem over here. It says over here, RS is tangent to circle C. So you have over here, you have RS is tangent at that position, and you have RT is tangent. So because both of those tangent segments stem from the same position, the theorem above says that these two have to be equal. Okay, so the given information says that RS is equal to 16. It also says that, we have some more here. TC is equal to 9. And they want to find what is the value of X, and then they want to know what is the value of CR. Okay, so let's go ahead and let's do this. All right, so we do have a little right angle here if I were to draw that. All right, so let's go ahead and solve this problem. It says that RS, again, is 16. X, we know that those are congruent, so we can say that X squared is equal to 16. And when solving, X is equal to the square root of 16. But remember, when you take the square root, it's a plus or minus. So this ends up being plus or minus 4. All right, so this one squared, again, we know it's 16. So that is your X value. All right, but now the question is asking us to find the value of CR. And by strategically drawing this way, we know we have a right triangle. We know that this is 16. We can go ahead, and I'm going to let you guys think about this one again. I want you to think about, what is it? TC is 9. Okay, so what would RC have to be? Okay, so if you wanted to go ahead and solve this, you're going to do the Pythagorean theorem. All right, I want you to finish this problem off. Okay, and you end up, and I'll get you started, but I do want you to finish this one on your own. You have RC squared is now let me put the other two first, leg squared. You have 9 squared plus your 16 squared, and then go ahead and solve, and let's see what you get. All right, so we're going to reconvene tomorrow. We're going to talk about this, and then we'll also do example 7 together tomorrow. But I want you to go ahead and at least get it started, see how far you can go. I do want the answer as a simplified radical. All right, so this will be part of your homework and part of our open discussion when we return together. Alrighty then. All right, you guys, that's a wrap on our notes for today. Make sure you take good, thorough notes, and then we'll have a conversation in our next meeting. Okay. Alrighty.